every single one of those in calculus next year, but there are some kind of cute proofs of 1 over n and its divergence that I'll point you to even today.
Wait, that says divergence with 2 r's.
That's just a few. It's all good. Okay. Where do we go here? This one here? I think this is where we need to be. All right. So one thing that unsettles me about this set of results is the following, right? It seems like, and I think some of you already have built this into your minds already, or you're thinking like, well, what's the last result, the geometric result, 0.53 plus 0.0053 plus 0.000053. Well, the terms themselves are getting basically to going to 0. So that must be what makes the series converge, right? Is that the terms must be getting infinitely small. But of course, now we see that that's not sufficient for explaining the convergence of a series. Witness the examples on the board, right? For all of these, the terms themselves approach 0, right? The thing you are adding out at infinity is progressively something closer and closer to 0, right? The 500th, the 1000th term of every single one of these is practically 0. So it doesn't seem to be enough. That doesn't tell the whole story. Sometimes that means it converges, and other times it means it doesn't. But we will say this, even though that test is not enough, it is, I want you to now think about the converse. What if we said the terms of a series I have in question go to something other than 0, like 5? I have this series where the thing I add gets progressively closer to 5. So that out at infinity, what you're doing is adding approximately 5 to approximately 5 more, and then you're adding approximately 5 more. The terms are not 5, but they're getting very, very close to 5. Would you like to say anything about the convergence of that kind of a series, that where the terms themselves, the thing we are adding, is getting progressively close to 5? Can you imagine doing that? Can you imagine claiming that it doesn't ever pass a certain number with a series like that? No, clearly, if we're always adding 5 basically out at infinity, it will burst whatever supposed sum you have that you've claimed for the series, right? So, although you might be thinking, well, if they don't go to 0, then that's 0 wasn't that test wasn't a very good test. Well, we're not completely wrong. Our hunch is actually pretty good. If the terms don't approach 0, then it is true that the series must diverge. But the reason this is called the nth term test for divergence is because the converse is not true, and you've seen that again on the board here, right? If the terms approach something like 5, then it definitely diverges. The series diverges. If the terms approach 0, though, apparently more testing is required, right? It's not enough to say that it converges. Does that make sense? We have to be very careful about how we use this. So it's not useless information to think about what the terms are approaching. It could, for us, identify a divergent series. That's useful. The mathematician would probably say that this is like the terms approaching 0 is like a necessary but not sufficient condition for convergence. Does that make sense? So all of these do pass that test, but obviously it's not a sufficient piece of information enough to know whether these actually converge. Okay, so let's think about the series that I have on the board, which is of a type that we haven't thought about at all yet. Sure seems promising, doesn't it? The terms seem to be getting smaller. They're all fractions smaller than 1. What do you think? Do you think that anyone want to wager a bet on this? Converge or diverge? And give your reason. Someone fight their case on this. Is that a hand thing?
Yeah.
Okay.
I think it diverges because when you get really large, you just ignore the negative ones. So it gets like pretty much 1/2 every time. So you're always adding half.
Yeah, do you agree with Cheyenne that out at infinity, this series is basically like, by the time you're out to like the term 1,000, it's like basically something very close to 0.5. Plus, the next term is still basically about 0.5. So this is the situation I was just talking about. So do you guys agree with him, or do you want to talk some more about it? No. Okay. All right, well, let's write it up nicely then. And I'd like for each of these today for you to write like a sentence in English that ends with a period. Okay. So here we go. Since the limit as n goes to infinity of n over 2n minus 1 equals, what did he say? 1/2, which is not 0. The series diverges by the nth term test. Again, it's worth underscoring time and time again that if the terms of a series do approach 0, you must use more testing to determine the convergence. But may you say that a series diverges by the nth term test, like we just did? Yes. Yes. But there will never be a time where you say, this converges by the nth term test. No. Don't do that. Okay, Ian, quick question. I think there are ways of doing sometimes that, but I'm not sure that's really ever desirable.
It's always desirable. What are you talking about?
I recommend to you a book by Bertrand Russell and Alfred Whitehead, where they do that. They prove on page like 500 that 1 plus 1 is 2 finally after like 500 pages of work.
Oh, yeah. I think
So the series we encountered yesterday, this slide is just review from yesterday. It's what I have written on the board there. And for more information, for including a couple proofs, I think I have 12 proofs posted here, of the fact that this series for p equals 1, the harmonic series, 1 over n, diverges. I have a link out there to a whole bunch of proofs, most of which I think are non-calculus based, but we will prove all of those things in calculus. So, but I think you're convinced that they're true, right? At this point, after having tested them. And we're starting to get like a little bit of a catalog of ways of testing series for convergence. So I have that catalog for you. When you get this, you'll recognize immediately the first 3 things in the catalog. All right, so I have really nothing more to say about these than what we've already said. Okay. So let's move on to the fourth, if you're keeping score here, the fourth thing in our catalog, the next test for us. And before we read it, it is reproduced up here word for word as it appears on your paper. Let's consider this series here on the board, 1 over n to the 4th plus 3. Now, if I just asked you, do you have a hunch about this series? What do you think? Do you think it converges or diverges? The answer can't be both. What do you think? I think that's a good hunch. Why is that your hunch, Corinne? Yeah, doesn't this feel, she says, doesn't it feel a lot like 1 over n to the 4th? And if 1 over n to the 4th, I hear you, right? If 1 over n to the 4th converges, well, this isn't that different. It feels like it. It feels like it grows at the same rate. The plus 3 doesn't really matter when n is huge, you're saying. I hear you, and that's correct. Let's see if we can we can write a little argument that goes in that direction. And then we'll come back to this in a second. Yeah, Cameron, you want to say something?
For that test, is there any positive convergent series that you suggest we use to compare it with?
Yeah, so I think that we've just found one, right, for this. And namely what? What did we say this feels like? This feels like 1 over n to the 4th. So let's see if we can come up with like a formal argument that kind of says what we just felt. So I'm going to start by saying, since n equals 1 to infinity, 1 over n to the 4th converges, let's take that as a given, because that's p equals 4, which is greater than 1. And, well, now we need to think a little bit more. How does this relate to the series that we actually have? I want you to think about term by term here. How do the terms, if you look at, say we plug 5 in, to this and to this, how do they relate? In particular, how do their sizes compare?
Well, overall, like in the long run, doesn't it not really matter? Because if you're always adding +3 to everything, then doesn't it mean like you're just like adding +3 to nothing because you're adding it to like every single one? So it doesn't like it just makes it like increases, but it doesn't actually like
Yeah, I need to have some more specificity to some of your words. You said add 3 to it, but I'm not sure what it means.
well, the terms that you get.
But each term here, it's not like you take these terms and add 3 to them to get these, though.
Well, no, but like never mind.
No, but I hear you. I want more specificity in our language. Again, the question is, how do these compare in terms of size in particular? Go ahead, Cameron.
Well, I guess if the first term specifically be to whatever 1 over n to the 4th, the first term for that would be 1. And then the first term for the sequence or the series that we have would be 1/3. And the pattern continues on and on for each term.
1/4.
Well, like
Whatever. Yeah.
well, like the denominator is always going to be smaller in that series than in the e to 1 over n to the 4th. So we know that each individual term when paired up with the 1 over n to the 4th, it will be smaller, which is what the direct comparison.
Oh, I haven't read this paragraph yet. That's true. Okay. So yeah, I mean, if we plug in 5, let me see if I can hear you on this. If you plug in 5 to both of these, do you agree? I think what Cameron's saying. Do you agree with him that if you plug in 5 to both of these, you get something smaller here than here? And there's nothing unique about 5. That's always true because he says the denominator is bigger here, and so this is always a smaller fraction than that is. Let's write that down. That is always smaller than that for all the n at least that we're thinking about. So I think you guys agree with me up to the comma. I guess I should strike the word so for the English language here. Since this happens, this converges also by DCT. Now, we haven't actually read the paragraph yet, have we? Let's stop and think about what that means. 1 over n to the 4th converges. So can you picture this in your mind? The series we have, 1 over n to the 4th plus 3, has terms that term by term are less than our series, right? Well, if this converges, then is it clear in your mind that this must converge too? You see in general that this is what the direct comparison test says, if you now read this with me. It says a series of positive terms is convergent if each term of the series is less than or equal to the corresponding terms of some other positive convergent series, period. So that's what we just discussed, right? We said if you have any series that I have in my possession that I know to be convergent, and then you bring me another series which always has, term by term, smaller values than my series, well then of course yours converges too. And in fact, if mine converges to S, yours converges to something less than S. Like we can even be more specific, right? And then read the second sentence. It just mirrors the first sentence. What does that say?
Bigger than a divergence is also divergent.
That is, if I have a known divergent series in my possession, and you come to me with a series that's term by term always bigger than my series, well then my divergence, yours must too. It has to, right? You're claiming that yours is going to converge? No way. No way. So now the only thing that we have to caution you against is that what happens if I have a divergent series, say, and you come to me with a series that's less than mine? What can be said? And the answer is, well, maybe nothing. Right? So be careful that you don't mix the two things up. Well, let's practice this sentence that we're writing, this justification on these two. This kind of, I think this approach might be fruitful here. What's the first one feel like? What do you have a hunch about the first one? Yeah, I think converge is a good feeling because it feels like what? Feels like it's kind of on the order of what? Yeah, it feels kind of like 1 over n to the fifth. It seems like if that should converge, which it does, then this should too. So again, let's write that formally. Here we go. So I might write something like this. Since 1 over n to the fifth, converges because p is 5, which is greater than 1, and 1 over 5n plus 5 to the fifth is less than 1 over n to the fifth, or n greater than or equal to 1. Let's stop there for a second. I just wrote that, but I haven't actually thought about whether it's true or not. Is that true, though? Can someone just assure me that that is true? Of course it is. You say of course like it's obvious. Is it obvious? I don't know. Why? Can you justify why that's true? Well, it's not always going to be true that this is going to happen, so I just want to make sure that we're clear on when it does happen, why it happens. If I needed more convincing in my mind, I might be like, well, I think that if n to the fifth is less than 5n plus 5, then this holds, right? Excuse me, to the fifth. If this is true, then this must be true, dividing both sides by the two quantities. And that is true if this is true, right? I'm just suggesting that if one wants to really prove this, you could, I guess. Well, but this is of course true because we assume when we start that n is greater than or equal to 1, right? So if n is greater than or equal to 1, then certainly this is true, which this follows from, this follows, and the result here follows. I don't need you to think that through every time like that. I just want to make sure you're like clear that like, yeah, this does actually make sense for real. For all n greater than or equal to 1. Okay. This series about this guy down here? Any hunch on this one? Converge? Diverge? Because it feels like what? So yeah, since this diverges, because it's p equals 2/3, which is less than or equal to 1, and our series, 9n to the negative 2/3, is always greater than the terms of the given series for n greater than or equal to 1, our series diverges too. By the DCT here, okay? Now I will note, by the way, that there's another way to justify that this diverges. You don't have to use a comparison necessarily. This is 9 exactly using properties of summation. This is exactly 9 times the P series, right? So if this is even defined, then this will be defined to be 9 times it. Well, this diverges, so I think it clearly follows even without the direct comparison test that this result holds. So every once in a while, I'll step back to and realize like what's actually happening. The series I'm now putting on the board is a little bit confounding. Stare at it for a second. So you realize that the tool we currently have fails. Do you see why? Yeah, the fact that this is, I mean, you're like, I think you were all right to think, oh, this converges, right? It's basically 1 over n to the 4th again, right? And yet, if we were to go to write this whole thing out and we were to say this converges because this thing is always less than 1 over n to the 4th, we would be wrong. Yeah, that's false. So this seems like the direct comparison test has a little bit of a flaw and a little bit of a weakness because we kind of know in our hearts that this row is like 1 over n to the 4th, and whether we subtract or add 3 here, it shouldn't matter. This converges too. So the idea of this idea can be captured. This idea of two functions of 2 sequences growing at the same rate can be captured in something called the limit comparison test. The question is, if you wanted to say that 2 things grew at the same rate, one way to think about that would be to say, if you think that 1 over n to the 4th and 1 over n to the 4th minus 3 grow at the same rate, then what I think should be true is that always, as you stack one term on top of the other, out to infinity, that they maintain some constant ratio, right? That one is just like kind of a multiple of the other out at infinity. You see how that's another way of capturing the fact that two sequences, the terms are growing at the same rate. And if out in infinity, this equals, that is out at infinity, as the limit as n goes to infinity, equals some number, then we've done it. We've showed that they grow at the same rate. So I think I'm ready to justify this. So since we'll start the same way, as n goes from 1 to infinity of 1 over n to the 4th converges because p is 4. And now here comes the change. And the limit as n goes to infinity of this stack equals, well, what does it equal? Have you actually figured it out? Which is a non-zero constant our series converges to. Why is it important that it be a non-zero constant? What would happen if you did this test and you got 0? What would that say? If we claim that these grow If these are growing at the same rate, we get a constant that's not 0. But what if we get a 0? What did that say about the relative growth rates of these two? Was one of them faster? Which one? No. The bottom one is faster if you get 0. What else is bad? If you get what? If you get, what would happen if the top one is faster than the bottom one? What would you get for the limit? What happens if this thing grows really big and this thing grows relatively not as big? What number, what do you approach? Yeah, infinity, right? So if we get 0, that's a problem. That says that the bottom one grew faster. And if we get infinity, that's a problem because that says the top one grew faster, and we haven't made our case. But if we get a constant, then we have showed that they do grow at the same rate. If one converges, the other must. And one diverges, the other diverges, right? Now, I should warn you, you can't yet do 2, 4, or 6. You have very little homework tonight. I apologize. Okay? You should be able to do the other 5, though.
No, please, you have one too. I know
You took it back.
Anyone not get the homework? What, man, did you get one?
Yeah, I got it.
Everyone get the homework? Anyone need it still? Did you get one? Okay. Did everyone in the back get a homework? Varun, did you get a homework assignment? Yeah. Okay. All right, bye everybody. May